Here's something that will ruin your day. Everything you've ever touched, every person you've ever loved, every star in the night sky, every galaxy sprawling across cosmic space, all of it combined makes up just 5% of reality. 5%. The rest? We have absolutely no idea what it is. Now, you might think, okay, scientists are working on it, we'll figure out eventually. But here's where it gets genuinely disturbing. We're not just slightly off in our calculations. When quantum physicists try to predict the energy of empty space, literally nothing, they were wrong by a factor of 10 to the power of 120. That's not a typo. That's a 1 with 120 zeros after it. To put that in perspective, if you predicted your morning coffee would cost $3, but it actually cost more than all the wealth that has ever existed in the entire observable universe, multiplied by itself several trillion times, you'd still be closer to the truth than our best physics. And this isn't some obscure corner of science. This catastrophic failure sits at the heart of cosmology. It's called dark energy, and it makes up roughly 68% of everything that exists. It's literally tearing the universe apart right now, accelerating galaxies away from each other at increasing speeds, and we have no clue why. If we don't solve this mystery, we don't just fail to understand the cosmos. We fail to understand the ultimate fate of time itself, the future of consciousness, and whether reality is even what we think it is. So buckle up. We're about to explore the biggest unsolved mystery in all of science. The thing that proves we're basically children pretending to understand a universe that laughs at our equations. Let's start with what we do know, or at least what we think we know. When astronomers began carefully measuring the rotation of galaxies in the 1970s, they discovered something deeply strange. Galaxies were spinning way too fast. The stars at the outer edges should have been flung into space like children on a broken merry-go-round. But they weren't. The math only worked if there was something else, something invisible, providing extra gravitational glue. We called it dark matter. It makes up about 27% of the universe. Now, dark matter is weird. Don't get me wrong. We can't see it, can't touch it, and have never directly detected a single particle of it. But at least it makes intuitive sense. It's just matter, stuff, invisible stuff that pulls on things gravitationally, like normal matter does, just more of it. Our brains can handle that. It's like discovering your house has been built on a foundation you never knew existed. Surprising? Yes. Reality breaking? Not really. But then there's dark energy. Dark energy doesn't just hide from us. It actively defies logic. While dark matter pulls things together, dark energy pushes them apart. It's not just invisible. It's anti-gravitational. It's the cosmic equivalent of discovering that your foundation isn't holding your house up. It's actively trying to rip it into pieces and succeeding. The discovery that broke everything came in 1998. Two teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic measuring sticks. They were trying to figure out how fast the universe's expansion was slowing down. Because of course it was slowing down, gravity pulls everything together. So the Big Bang's initial expansion should be gradually decelerating, right? Wrong. The universe wasn't slowing down, it was speeding up. Imagine throwing a ball into the air, and instead of falling back down, it accelerates upward, faster and faster, with no rocket, no engine, nothing pushing it. That's what the universe is doing. Every second, the space between galaxies grows larger, and every second, that growth accelerates. The discovery won the Nobel Prize and triggered an existential crisis in physics that continues today. So what is dark energy? The most popular explanation is something called the cosmological constant, a term Einstein himself introduced, then abandoned, then had posthumously resurrected like some kind of mathematical zombie. Here's the idea. Empty space isn't actually empty. Even in a perfect vacuum, with no atoms, no particles, no nothing, quantum mechanics tells us there's still energy. Virtual particles pop in and out of existence. Quantum fields fluctuate. The void seethes with activity. This is called vacuum energy, and here's where things go catastrophically wrong. When physicists try to calculate how much energy empty space should have based on quantum field theory, they got an answer. When cosmologists measured how much energy it actually is based on the universe's expansion, they got a different answer. How different? The predicted value was 10 to 120 times bigger than the observed value. This is called the vacuum catastrophe, and it's not just the worst prediction in physics. It's the worst prediction in the entire history of science. By comparison, every other scientific theory is stunningly accurate. The standard model of particle physics makes predictions accurate to 1 part in a trillion. General relativity predicted gravitational waves a century before we detected them. But vacuum energy? We're not even in the ballpark. We're not in the same galaxy as the ballpark. We're not in the same observable universe as the ballpark. Something is fundamentally, horrifically wrong with our understanding of reality. Now here's what makes this truly mind-bending. Dark energy means that nothing is actually something. Empty space has weight, has energy, has consequences, and because space itself is expanding, there's constantly more space coming into existence. More space equals more vacuum energy. More vacuum energy equals more dark energy. More dark energy equals faster expansion. Faster expansion equals even more new space. It's a feedback loop. Nothing is creating more nothing, which is creating more of the something that is nothing, which pushes everything apart to make room for more nothing. If your brain hurts, congratulations, you're beginning to understand the problem. And here's the truly weird part. Dark energy doesn't dilute. When a universe expands, matter spreads out and becomes less dense. Radiation spreads out and becomes less dense. But dark energy stays constant. Every cubic meter of space contains the same amount of dark energy, no matter how much the universe grows. Which means, over cosmic time, dark energy wins. Eventually, it will be the only thing left. If you enjoy our videos, we would love for you to subscribe and like them, and we would be immensely grateful for your comments. Think of the universe as a cosmic tug-of-war. On one side, you have gravity, the attractive force generated by all matter and energy, pulling everything together, trying to collapse the cosmos into a singular point. On the other side, you have dark energy, the repulsive pressure of space itself, pushing everything apart, trying to isolate every particle from every other particle. For the first few billion years after the Big Bang, gravity was winning. Matter was dense enough that its gravitational pull dominated. Galaxies formed, stars ignited, planets coalesced, structure emerged from chaos. But dark energy was patient. As the universe expanded, matter spread out. Its density decreased, its gravitational influence weakened. Meanwhile, dark energy remained constant. Same strength, cubic meter after cubic meter, relentlessly accumulating as new space came into existence. Around 5 billion years ago, the balance tipped. Dark energy overtook matter. The universe's expansion, which had been decelerating, began to accelerate. For your animator, imagine galaxies as points of light connected by strings. Initially, gravity pulls them together, the strings taut. Then the strings begin to stretch, slowly at first, then faster. The galaxies don't move through space. Space itself expands between them, carrying them apart like raisins in rising bread dough. This is why distant galaxies appear redshifted. Their light gets stretched like a rubber band as space expands during the light's billion-year journey to our telescopes. The farther away a galaxy is, the faster it's receding, the more its light shifts toward the red end of the spectrum. There are galaxies we can see right now whose light is so redshifted they're disappearing into the infrared, beyond the reach of optical telescopes. And there are galaxies beyond our cosmic horizon, galaxies whose light will never reach us because the space between us is expanding faster than light can travel through it. Let that sink in. There are parts of the universe that are forever invisible to us, not because of any physical barrier, But because of geometry itself, dark energy has created walls of distance that even light cannot cross. And those walls are closing in. So what does this mean for the future? Let's fast forward a few trillion years. The universe continues expanding. Galaxies that aren't gravitationally bound to our local cluster accelerate away. One by one, they cross the cosmic event horizon and vanish. Their light, stretched beyond infinity, simply ceases to arrive. Eventually, give it 100 trillion years, every galaxy outside our local group will have disappeared. An observer in this distant future would look up at the night sky and see almost nothing, just a handful of nearby galaxies merged into one megagalaxy, floating in an ocean of perfect darkness. All evidence of the Big Bang, gone. All evidence of cosmic expansion, gone. All distant galaxies vanished. An astronomer in that era would have no way of knowing the universe was anything other than one island of matter surrounded by infinite void. They would be profoundly, cosmically wrong, and have no way of discovering their error. But it gets worse. As the universe continues expanding, stars run out of fuel. One by one, they die. The last red dwarfs flicker out. Black holes evaporate via Hawking radiation over googolls of years. Eventually, even the protons in dead matter decay. This is called heat death, the slow, cold, inevitable slide into maximum entropy. The second law of thermodynamics states that entropy, disorder, randomness, the evening out of energy, always increases in a closed system. The universe is the ultimate closed system. Every process, every thought, every star's fusion, every heartbeat increases the total entropy. And you can't reverse entropy. You can't unscramble an egg. You can't unburn a log. And you can't rewind the cosmic clock. Given infinite time, the universe reaches a state of thermodynamic equilibrium. No temperature differences, no energy gradients, no fuel for any process, just a thin, cold fog of elementary particles spread across exponentially expanding space, too far apart to ever interact again. Nothing happens, nothing can happen, nothing will ever happen again. But there's an even worse possibility, the Big Rip. If dark energy isn't constant, if it's actually increasing in strength, then the acceleration doesn't just expand space between galaxies. Eventually, it tears apart galaxies themselves, then solar systems, then planets, then molecules, then atoms, then even the nuclei of atoms, the fundamental particles, space-time itself. In this scenario, there's a finite deadline, maybe 22 billion years from now, maybe more, maybe less, but on that day, the fabric of reality shreds. Every structure, every bond, every quantum field ripped apart by runaway expansion. The universe doesn't fade to black. It tears itself to pieces in a final catastrophic instant. For your animator, a galaxy, serene and spiral. Then the edges begin to fray, stars pulled from their orbits. Then the stars themselves distorting, stretching, planets torn from their suns. Then the planets fragmenting, zoom into Earth, continents ripping apart, oceans vaporizing, people, buildings, atoms, all elongating like taffy, then disintegrating into quantum noise. Finally, reality itself pixelates and shatters. We don't know which fate awaits us, heat death or Big Rip, slow freeze or violent shred, but both end the same way. In a universe where structure, complexity, and consciousness are impossible, dark energy, this thing we don't understand, is writing the final chapter of existence itself. So where does that leave us? Here we are, tiny biological machines on a wet rock, staring into the abyss of our own ignorance, confronted by a force that comprises 68% of reality and makes absolutely no sense. Some physicists wonder if dark energy is evidence we're living in a simulation, a cosmological constant manually tuned by some higher intelligence to allow galaxies and stars and life to exist. After all, If dark energy were slightly stronger, the universe would have torn apart before stars could form. Slightly weaker, and everything would have collapsed into black holes. The value seems fine-tuned. But that raises more questions than it answers. Fine-tuned by whom? For what purpose? Others suggest we're simply wrong about gravity. That general relativity, magnificent as it is, breaks down at cosmic scales. That we need a new theory, quantum gravity, modified gravity, something we haven't imagined yet. Or maybe there are extra dimensions we can't perceive, and dark energy is gravity leaking out of our universe in a higher dimensional space. Or maybe multiple universes are pressing against ours, and dark energy is the pressure of their existence. Every explanation sounds like science fiction because we're genuinely lost. But here's the thing. Our ignorance is not a failure. It's the frontier. Every great leap in human understanding started with a mystery that seemed unsolvable. Newton couldn't explain why gravity worked, just that it did. Einstein couldn't reconcile quantum mechanics with relativity, and we still haven't. The discovery of DNA didn't immediately explain consciousness. Dark energy is the current edge of that frontier. It's the question so big, so fundamental, that answering it will require a revolution in physics as profound as relativity or quantum mechanics. Somewhere, right now, there's probably a graduate student staring at an equation, or an astronomer analyzing telescope data, or a theorist pursuing a wild idea that their colleagues think is crazy, and they might be standing on the edge of the answer. When we solve dark energy, we won't just understand the fate of the universe. We'll understand the nature of space, time, and existence at a level that makes our current physics look like cave paintings. And maybe, just maybe, we'll discover that the 5% of the universe we thought we understood was actually the aberration, and the 95% we couldn't explain was trying to tell us something beautiful and terrible and true about the nature of reality all along. Because remember, everything you are, everything you know, every law of physics that works, every prediction that's ever been verified, all of it exists in that tiny 5% sliver of reality. The other 95%? That's the universe we haven't met yet, and it's waiting.